A computer does not see a dog, a face, or a sunset. It sees numbers. The strange part is that those numbers can still become understanding. When you look at a photo, your brain jumps straight to meaning. You notice the person, the mood, the place, and maybe even the story behind the moment. It feels effortless because your visual system has been learning from the world since birth. For a computer, the same photo begins as a flat arrangement of tiny squares. Each square stores a measurement of light and color. Before there is a cat, a car, or a tree, there is only a grid. A pixel is short for picture element. It is one addressable point in a digital image. On its own, a pixel does not know what it belongs to. It only has a position and one or more values that describe its color or brightness. Most color images are stored using channels, often red, green, and blue. A bright yellow pixel might have a lot of red, a lot of green, and very little blue, so the color you see becomes a small bundle of numbers. You can think of an image like a spreadsheet. The rows and columns mark locations. The cells contain values. A simple black and white image might need one value per pixel. A color image usually needs several values per pixel. Here is the first big misunderstanding. Pixels are not little pieces of objects. A pixel on the edge of a face is just a color value near other color values. The idea of face is something a model has to build later. The next step is to look at relationships between nearby pixels. A single pixel is weak evidence. A small patch of pixels can show an edge, a corner, a shadow, a texture, or a color change. This is where raw data starts to become structure. Imagine a row of pixels that suddenly changes from dark to light. To us, that might be the edge of a door. To a vision system, it is first a pattern of changing numbers. Detecting those changes is one of the earliest steps in visual understanding. Many vision systems use filters that slide across an image. A filter is like a tiny pattern detector. One filter may respond strongly to vertical edges. Another may respond to horizontal lines. Another may respond to a certain kind of texture. When a filter scans the image, it creates a new image-like grid called a feature map. Bright spots in the feature map mean the pattern was found strongly there. Dark spots mean it was not. The model is no longer storing just color, it is storing signs of patterns. If this kind of explanation helps you understand AI without the hype, consider subscribing. We are going step by step from simple pixels to the hidden math behind modern machine vision. One layer can find simple patterns. Later layers can combine those patterns into more useful features. Lines can become corners. Corners can become parts. Parts can become shapes that help identify an object. This is not how human vision works in every detail. Computer vision borrows some useful ideas from biology, but it is still a mathematical system. It does not experience the world. It transforms numbers into more useful numbers. A model does not automatically know which patterns matter. It learns from examples. During training, it sees many images and receives a signal about what it should output. Over time, it adjusts its internal settings so useful patterns become easier to detect. Inside a model are many adjustable numbers called weights. These weights control how strongly different signals influence the next step. Training is the process of changing those weights until the model produces better answers on the examples it sees. After many layers, the image may no longer look like an image inside the model. It becomes a vector, which is a list of numbers. This list is a compressed description of what the model has found important. That vector is often called an embedding. An embedding places the image into a mathematical space where distance can carry meaning. Images that the model considers similar often end up closer together. Images that seem different often end up farther apart. If two images both show golden retrievers, their embeddings may point in similar directions. If one image shows a dog and another shows a refrigerator, their embeddings may be far apart. The model is not comparing feelings, it is comparing numerical relationships. The hard part is that real embeddings often have many dimensions. We can draw 2 dimensions on a screen and maybe imagine 3. A model can use hundreds or thousands. Each dimension is not always easy to name, but together they create a useful structure. Latent space is the hidden space where these compressed representations live. The word latent means hidden. It is not a secret room inside the computer. It is a mathematical arrangement of points that captures patterns the model learned from data. A latent space is like a map, but not a map of physical streets. It is a map of similarity. Nearby points might share colors, shapes, textures, object categories, or more abstract ideas. The exact meaning depends on how the model was trained. Sometimes directions in latent space can correspond to meaningful changes. Moving one way might make an image representation more like a daytime scene. Moving another way might make it more like a close-up. But these directions are learned patterns, not human labels carved into the system. This is why embeddings are useful. Once images become points in a mathematical space, computers can search, sort, cluster, compare, and retrieve them. A photo library can find similar images. A safety system can detect unusual frames. A robot can compare what it sees with what it expects. Modern systems can also connect images with text. A model can learn that a picture of a red bicycle and the words red bicycle should land near each other in a shared representation space. This lets the system search images with words or describe images using language. One common task is classification. The model receives an image and chooses a label, such as cat, truck, or mushroom. But classification is only one use of vision. The same basic idea can support search, detection, segmentation, captioning, and generation. Detection asks not only what is in the image, but where it is. The model may draw boxes around people, cars, signs, or animals. This requires the system to keep spatial information, not just a final summary. Segmentation goes further. Instead of drawing a box, it tries to assign pixels to regions. One region might be road, another might be sky, another might be a person. This is useful when the exact shape of an object matters. Image generation uses a related idea in a different direction. Instead of only turning an image into a representation, a model can start from a representation or a text prompt and produce pixels. It has learned connections between patterns in latent space and patterns in images. Every representation leaves something out. A good embedding keeps information that helps the task. It may ignore details that humans care about, such as a tiny logo, a subtle expression, or the exact layout of objects. Compression is powerful, but it is never neutral. A vision model may learn shortcuts. If most training photos of boats contain water, the model may rely too much on water. If most photos of an object come from one angle, it may struggle with other angles. The model learns patterns from data, including accidental patterns. Humans often recognize objects by overall shape and context. Some computer vision models can be surprisingly sensitive to texture. A strange image with the shape of one object and the texture of another may reveal that the model is using different clues than a person would. Because models operate on numbers, small changes can sometimes have big effects. A tiny pattern that looks harmless to us may shift the model's internal representation. This does not mean vision AI is useless. It means mathematical perception has failure modes that human perception may not share. Researchers use visualization tools to study what parts of an image affect a model's decision. Heat maps can show where the model focused. Feature visualizations can show patterns that strongly activate parts of the network. These tools help, but they do not make every decision perfectly transparent. So the journey goes like this. Light becomes pixels. Pixels become local patterns. Patterns become features. Features become embeddings. Embeddings live in latent space. At each step, the image becomes less like a picture to us and more like a structure the computer can compare and use. The deepest idea is that computers do not need to see the way we see to do useful visual work. They need representations that preserve the relationships needed for a task. Modern AI vision is not magic sight. It is learned mathematical structure built from examples. Next time you see an AI recognize an image, remember what is happening underneath. It is not staring at the world like a person. It is translating the world into numbers and navigating a hidden map. If you have questions or want a future video on image generation, vision transformers, or embeddings, leave a comment below.